Now we'll see the next algorithm, that is Dijkstra algorithm. Dijkstra algorithm is better than Bellman-Ford algorithm. Did you remember? Bellman-Ford algorithm took order of EV time, right? So this Dijkstra algorithm is going to take better than that. We'll see how much it is. Before that, we'll see what is the working principle of this Dijkstra algorithm. So in Dijkstra algorithm also, we are going to use D matrix and pi matrix. Pi to remember the knowledge giver's name, otherwise who teaches the best answer. Second one, distance matrix to remember the shortest path from source, right? So these are the two things. So but the difference between Bellman-Ford and Dijkstra is the way that D values are updated and the way pi values are updated. Of course, pi values are updated in the same way like Bellman-Ford, but what is the way these D values are updated? There is a different order here. Okay, we'll see that. So finally you remember one thing, in Bellman-Ford or Dijkstra, so we update D values only based on that relaxation step. Only that relaxation step is going to update the values. But here, how these relaxation steps will be done, we will see. Let's begin with Dijkstra algorithm. In Dijkstra algorithm, first of all, so this is the D matrix I am showing here. These are the contents of D matrix before algorithm begins. We know that. So source, let's say A is source vertex. So if A is source vertex, then distance of A is 0, right? Already it got shortest value. But B, C, D are not knowing the correct answer. We have to teach B, C, D. Who is going to teach B, C, D is the question in Dijkstra algorithm. So for that, always what we do is in Dijkstra algorithm, rather than relaxing every edge like Bellman-Ford, did you remember that? In Bellman-Ford, we relaxed every edge. How many times? V minus 1 times. We don't do it. Here we do it in a careful way. So first, what we say is, A is already knowing the shortest path, right? So we say that A is, the best person to teach others. Directly now we use A and only we relax A. That is the order we follow. First we relax A in this step. If I relax A, what happens? All the edges of the A should be relaxed. So let me do that. Let's take randomly the edges. Okay. So A to B edge, any order we can take. Let's relax A to B edge. What is the formula for relaxing? So using A to B edge, if I relax, then whom going to be relaxed or updated? B, right? Formula for that is we compare distance of A plus weight of this AB, this versus old distance of B, correct? What is the old distance of B? Currently infinite. If we get better value with distance of A plus weight of AB, so distance of B is going to be updated. Distance of A currently is 0 plus weight of AB. What is weight of AB? 3, right? So directly I can say 0 plus 3, which is better than infinite. Then here B value will be updated. So this is same, right? Now after that we relax another edge. Do we have any edge? Yes, we have AC edge, AD edge. Everything to be relaxed. Let's relax AD edge. Anything is possible. So A to D edge. What is the value of that? 7. So because of that, D is going to be updated. What is D value? Infinite, right? Distance of D. So obviously we can understand that distance of A plus weight of AD is now distance of A 0 plus weight of AD 7, which is better than infinite. So distance of D will be updated to 7. After that, we are going to take one more edge, that is AC edge. Sorry. So AC edge is having 8 weight, correct? So if I relax it easily, now by this time you should get experience. What is that? Distance of C should become 8. Think about it. Weight of AC versus distance of C. Distance of A 0 plus weight of AC 8. So that 8 is definitely less than this infinite. So update it. That's it. This is the second, I can say the first pass in Dijkstra algorithm. Now we are going to select one more person to relax. Just now A got relaxed, right? This time we have to pick up the next vertex to be relaxed. On basis of what? In Dijkstra algorithm, that is very important. First of all, you have taken A based on the shortest value among all. Since A is having shortest value, so that's why A is selected. This time also among all this, B, C, D. So now don't relax A. Otherwise, don't select A at any time. That's why I am marking it. Let's mark it. So A will not be considered. The reason already A got shortest distance, no need of relaxing him and no need of taking him. Now we have B, C, D. So what Dijkstra algorithm does is, this time it will pick again a vertex whose D value minimum. Okay, that is what we are going to do every time. So this time 3 is minimum, right? Then B is going to be relaxed. Relaxing B is nothing but relaxing all the edges of B. So if I relax B's edges, then it will be BC, second one BD. Let's teach C. Mr. C, what is your value now? 8. But I have a better answer, I think. What is that? Distance of B. I know source, that is distance of B, which is 3 plus weight of B comma C versus distance of C. Okay. So distance of B is how much? 3 plus what is weight of BC? Weight of BC is 1. 3 plus 1, which is definitely better than distance of C. Correct? 8. So update it. So this will become 4. Now BC edge is relaxed. Let me list out all the edges to be relaxed. BC, after that BD. We have only 2 edges. Let's relax BD. If I relax BD, what happens is distance of B plus weight of BD versus distance of D. Distance of D is 7. Distance of B is 3, right? Plus weight of BD. Weight of BD is 3. 3 plus 3, 6 is better than 7. Update it. So it becomes 6. So in that way, all the edges of B are relaxed. Now what to do? Then write the remaining values. This is the status of D matrix. Now A and B are already marked. So they got relaxed. Now we have to pick up a vertex whose value is minimum, whose D value is minimum. 4 and 6. Which one? C. Then C is going to teach others. Now we have to relax all the edges of C. Let's relax all the edges of C. So C got only one edge, which is C to D. Let's relax it. So distance of C. Okay. So plus, this is C time, right? Distance of C plus weight of CD. If I do that, what happens? What is distance of C? Distance of C is here 4 plus weight of CD 5. So 5, and what is the old value of distance of D? 6. 5 versus 6. Which one is better? 5. That's why distance of D will be updated. There is only one edge from C, correct? C to D. That's why only one value will be relaxed, or only one edge will be relaxed. 0, 3, 4, 5. This is the answer. Now first A, after that B, after that C. Right? So next time D has to be relaxed. Okay. So the reason already A, B, C are gone. One more reason among them. What is the minimum value now? D value, because we should not take A, B, C. Correct? Already they are considered. So we are going to relax D. But generally it is not required. The reason is, so A, B, C, whenever they are selected to relax, by that time already they got shortest distances. That is the one important property of Dijkstra algorithm. You remember it. Example, what I am saying is, initially you fixed vertex A, correct? This is called fixing. You fixed a vertex A. So obviously we fix source vertex. At that time it got shortest distance, right? That's obvious. Second time you fixed B, right? By that time B got shortest distance. After that, that's value is not changed. If you have a doubt, you check in the picture. See, what is the shortest distance of B? 3, right? So that's fine. B's shortest value it got when it is fixed. And after that we fix C, but by that time definitely C will get shortest distance. Now after that you are going to fix D. So by that time, so D is also going to get shortest distance, but everyone got the shortest distance. Then why to relax D? Correct? So you don't really require to relax D, because all others already got the answers, right? So that is the Dijkstra algorithm. Let me summarize about Dijkstra algorithm. There are 2 steps. What we do is, first of all, we take distance values for every vertex and we pick up the minimum distant value, right? A vertex with minimum distance. So that is called fixed vertex, and we are going to relax all the edges of that vertex. Once you do it, then D values may be updated. After that, you have to pick up again one more vertex based on the D values. Which vertex will be picked up always? A vertex whose D value is always minimum. But don't consider the previous vertex. That means don't consider the vertex which already fixed. Okay. So you tell me, since we are picking up a vertex with minimum key value here key values are D, correct? So what is the best data structure to always pick the minimum from some list of elements? Definitely min heap. So we need min heap for that. And one more thing, we have to update these pi values. How these pi values are going to update it, we'll see. First of all, we fix A, right, as a fixed vertex, and we are going to relax. In this step, what happens after relaxation? So this value got updated, right? Then when B value got updated through A, because of A, B value got updated. So we update like this. Mr. B, you got D value 3 because of A, remember him. Mr. C, you got a value called 8 in the D D matrix because of A. In that way, when you fix A vertex, here entire in everywhere we write A. Anyone got updated D? D also gets A. Then this one will become, what is the value? 7. In the second phase again, who got updated this time? C. When D is relaxed, C got updated, D got updated. So in the next step, so in the place of B, C got updated, right? So what is the value? Value is 4. Mr. C, new value is 4 and that is because of B. In that way, so this pi value will be updated every time, right? Depends on the values. Now this value will be again updated to B and this value will become 6. In the next step, when C is relaxed, what is going to happen? You see, someone got 5 and no one got updated. Only D got updated because of C. Mr. C, so you are updating D and the value is 5. So D says thanks to C and it updates C, correct? In that way, pi values are updated. So what we do is, I take another example of graph, and rather than this matrix form, I take a heap form, because in implementation we maintain min heap, right? So I will take all the data structures, min heap and D array, pi array, and I will teach you how that array and heap are going to be updated, so that we can understand the time complexity of Dijkstra algorithm easily. Okay. Now we'll see the time complexity of Dijkstra algorithm. To understand it clearly, I will teach you what are the data structures used by that algorithm. So these are the things we are going to use in this Dijkstra algorithm. One is this graph. This is only for us, for our imagination, but this is adjacency list. Okay. Example, whenever you have a graph, we'll have this adjacency list, and see here, there is edge from 1 to 2. Then there is an edge from 1 to 2. What is the weight of that? 1. I represent in another location in that way. Similarly, there is another neighbor for 1 who is 5. So we maintain one box on that vertex and corresponding edge weight. So the edge weight is 7. In that way, we maintain for all the vertices. So this is clear. Now this is min heap. So already I told you, every time we are going to pick up minimum D value. For that, I am going to create a heap of D values. And this heap is connected to D array. So this D array and this min heap are going to maintain same value. So sometimes I am going to update D values, right? Whenever I update D values, I am going to update in heap also. We will see that. So we will have a pi array. This pi array is only to maintain who is going to teach us the best value, right? Every vertex will maintain that. So pi also contains 5 locations, because graph contains 5 vertices. Initially, now initialization. Initialization is like this. D of 1 is 0, which is 1 is source vertex, that is my assumption. Then all other D of 2, D of 3 will be infinite. So pi will be initialized to null, 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 null initially, because nobody knows any value, right? So initially we don't know best value. So this 1, 2, 3, 4, 5, pi 1, pi 2, pi 3, pi 4, pi 5 will be updated while running the algorithm. We know that, correct? Let's begin. What is the first step in this Dijkstra algorithm so far? So we just initialize some data structures. These are the data structures initialized. We are going to use them, and what is the flow in Dijkstra algorithm is pick up the minimum D value, correct? So these are the D values. So delete here in this heap to find out the minimum value. This root will be the minimum value, correct? You just delete it. Why? Because next time we should not have it in the heap, correct? Because this vertex example 1, right? We are going to fix vertex 1 now, and we are going to relax it. That's the reason I am picking minimum value from the heap. Why I have to delete it? The reason, next time I should not consider anything about 1. That means I am not going to update 1's value after 1 is deleted, correct? That's why you permanently delete it. So if I delete this one, so what happens? Immediately whenever this value is deleted, go to the membership matrix and make it 0. That means 1 is no more in the heap. So once 1 is deleted, so this tree will be disturbed, right? We have to adjust it, correct? So what we do is we adjust it quickly. So we know how to adjust it, correct? So if you adjust it, what happens? You will get a heap with 4 values. So D of 2, D of 3, D of 4. Let's assume that this is D of 2, because all are infinite values, correct? D of 2 infinite, D of 3 infinite, D of 4 infinite, D of 5 infinite. So we can assume heap like this. Okay. So this is, let's say, D of 3 and D of 4, D of 5. Whenever you update the heap, the corresponding pointers, example, the node 2 was here left side, it was moved here. then the link also should be moved properly, so that this will always link to d of 2 location in the array, right? Now finally I deleted one node from the heap. What should I do next? Once you delete a node, we say that we fixed a vertex. So once we fix the vertex, the second step is just relaxing all the edges of that. We have a number, what is that? 1, right? So relax, go to this adjacency list and go to the corresponding link list and take every edge from it and relax it one by one. First relax 2, that means 1 to edge. We have value also, right? So take 1 to edge, which is value is 1. So what is the formula to relax? Like this. I am relaxing 1 to 2. Formula is distance of 1 plus weight of 1 to versus distance of 2. So distance of 2, see now, what is better thing to access distance of 2 in this array or this array, this heap? So locating d of 2 in the heap will be very difficult. That's why I am also maintaining array. That is the purpose of maintaining another array. Now d of 2 is easy to access here, constant time. So distance of 1 we can access here 0 plus weight of 1 2 is what? So this is relaxation step. Weight of 1 2 we have here 1. 0 plus 1 1. Distance of 2 infinite. So 1 versus infinite. So definitely 1 is lesser than infinite. Then we update d of 2 value. Where we update? It is easy to update here, correct? But whenever you update here, we have to update it in the heap also. Directly go to the heap and update it. If you have a doubt whether 2 is in the heap or not, directly go there and check here. 2 is there in the heap, right? Yes. Otherwise, directly, yeah, it is there. Directly we can check here within constant time. That is the advantage of membership matrix. Whenever you have a doubt whether one element present in the heap or not, now at this moment I have a doubt, really 2 is present in the heap or not. So I directly go there and I take the link. So I'll come here. That is better. Now adjust the heap. Correct? So what is the value we have to write? D of 2 value now 1. Whenever you write value, that's why. So did you remember in Bellman-Ford algorithm we did not maintain this one. So whenever d values are updated, so we just updated and we kept quiet. But here we have to update d values and corresponding heap values also, so that always heap maintains minimum d value. So you adjust the heap. So because already this value is minimum, so it is already in min heap position, but of course doesn't matter. We have to adjust it, right? Then after that, what to do? Go to the another edge, which is 1 5 edge, correct? So what is the value? 7. Apply relaxation step again. Distance of 1 plus weight of 1 5 versus this time distance of 5. First, what is distance of 5? Definitely infinite. Distance of 1 0 plus weight of 1 5 7. So 0 plus 7 is 7. 7 versus infinite. Which one is better? 7. So update distance of 5. So it will become 7. When it becomes 7, immediately go to the heap and we have a pointer from here to here. Within constant time I can reach here, I can update it, then I again update this heap, right? Whenever a key value is updated because of relaxation step, heap should be updated. So simple, right? So after that, if you update it, what happens? Distance of 5 will go up, correct? So you know how to update heap. So I'm not discussing that now. So here it will be distance of 3. It will become infinite. This will become 7, right? So finally it will be settled like this. Then relaxation step is done, right? All the neighbors of 1 are relaxed. After that, what to do? Second step in the Dijkstra algorithm is picking up the next minimum. Who is next minimum? Go to the heap, you can find out. So always the next minimum will be on top. Delete the top element, do the same process, correct? Now, so whenever you delete this time, I'll show just, if I delete it, so he is going to be the second minimum, correct? And again you continue. And this pi value should be updated properly. When to update these pi values? Whenever a vertex d value is updated, example you updated d of 5, right? So whenever you updated d of 5, immediately go to pi of 5. Based on what value you updated d of 5, who taught us? Vertex 1, right? Right 1. So you updated 1 also. At that time immediately you make pi of 2 to 1. So it takes only constant time, correct? So this updation take only constant time. So this is a process. Delete the element now, relax this time, the value is 2, right? Go to adjacency list directly, this 2, and relax all the edges. After that, maybe another vertex will be picked up from the heap, again relax it. In that way every vertex will be relaxed. Then Dijkstra algorithm will be completed. This D array is going to have all the shortest distances. That's it. This pi matrix is going to have all the parents of the, all the parents. Parent means here, so the vertex, example pi of 2 is nothing but a vertex who gave us the right information about otherwise shortest distance about 2. So if I backtrack them like DFS, did you remember? Then I can get all the shortest path. Example, let's say for 5, shortest path we got from 1, right? That means I can backtrack like this. Mr. 5, who gave you shortest path? 1. That means you learned it from 1. That means because of this edge. So this will be part of the shortest path. Now I can definitely say that shortest path is 1 to 5. In that way, so these pi values are going to help us to find out the shortest path. That's why we maintain it. Now we will see the time complexity of this Dijkstra algorithm. Now we'll see the time complexity. What are the things you did finally? We did something repetitively. What is that is? First step immediately you did is initialization, correct? So once initialization is done, then after that second step is fix the vertex. That means you select the vertex from the heap. Okay, top element of course, right? Root element. Fix the vertex and relax it. So you know how to relax it, correct? In the relaxation, we know the time complexity also. Once when you are relaxing it, update heap values, correct? Sometimes update heap values. Whenever some value D here, whenever you are relaxing, if some D value is updated, corresponding heap should be updated. That's it. So that is updating the heap. Now anything else? Again go to the, it's a loop, right? So while your queue is not empty, keep on doing fixing the vertex, relaxing it. That's it. Now easily we can understand the time complexity. What is initialization? This one. Creating a membership array and writing 1 1 1 1 1. How many vertices we have? V, right? Then that takes V time. Fine. Next. In initialization, we initialize this to 0, infinite, infinite, infinite. It takes V time. Now, pi matrix will be initialized. It takes V time. After that, anything else? So, we create a heap, right? So, the time complexity of creating the heap, let's take here. Time complexity of creating heap, already I told you, with V vertices, it takes order of V time, right? Now, after that, story begins. First step, we write while loop, right? While queue is not empty. How many times this loop will be checked? Whenever queue is not empty, what are you going to do? We are going to delete definitely one element from the heap, correct? See here, queue is nothing but min queue, heap, okay? So, how to check queue is empty or not? Checking that directly go to that heap tree. If that heap tree is null, then queue is empty, correct? So why I am representing heap as queue? Already I told you, heap is nothing but priority queue. That's why we use a symbol queue. Otherwise, you can say while heap is not empty, not an issue. So whenever heap is not an empty, we are going to the loop, and what are you doing? You are fixing the vertex. Fixing the vertex is nothing but deleting one vertex from the heap. We are not at all inserting any element in the heap. Always we are deleting. Initially you had V vertices in the heap. Every time if you are deleting one vertex, then while loop will be terminated after V times, correct? So while never runs for infinite time. Why? When you come inside the while loop, you are deleting one element. You have initially V vertices. Every time if you delete one vertex, then vertices will be exhausted, right? And we are not inserting anything. So V times. Happily I can say that it takes only V units of time. Now, after that, fixing the vertex. What is the meaning of fixing the vertex? Deleting it. What is the time complexity of deleting a node from the heap? Log V, correct? Where V is the total number of vertices. Height of the heap tree is log V. So, fixing the vertex takes log V time, remember. But how many times you are fixing the vertex? Only one time? No. Sir, in the while loop, every time I delete the vertex, V times I do, correct? Almost. Not exactly V, but V minus 1. Doesn't matter, right? Let me approximate it to V log V. So V times we delete a node from the heap. So it takes approximately V log V time. I am assuming every time tree height log V. That may not be true. Sometimes, after every iteration it will be reduced. But if you simply, so many times we have seen when you have a heap, if you delete V elements from the heap with initial height of log V tree, it takes V log V time. We have seen so many times, correct? So V log V. I safely assume that it is V log V. After that, relaxation. So how many times you do relaxation? V times, because every fixed vertex is relaxed. Then can I say like this, when first time vertex number 1 is relaxed, you are traversing this list. When 2 is relaxed, this you are traversing the list. 3 is relaxed, you are traversing the list. Let's clearly understand relaxation. Traverse the list, take an edge and apply this formula, relaxation formula. It takes constant time, right? Now after that, if anything to be updated, go to the array and update the value, and go to the heap and update the value. All of the things you are doing, okay? So I can say that overall in this relaxation step, you traversed overall graph, right? It takes v plus e time, I mean total, right? Let's do all the calculations one by one. So in this process, we traverse the graph, done. Anything else you did? Yes, we did. Once you pick up an edge, how many edges we have overall? E edges. So for every edge, you try to apply this formula. What is that formula? Distance of u equal to plus weight of uv versus distance of v. This formula you applied, correct? It takes 1 unit of time. So how many times you applied this formula? E times. That takes e into constant time, correct? Yes. Assume that every time this formula condition become true and you updated d value every time. That's possible, right? Example, so because of 1, 2, 5 got some values. Then after that 2 came, 2 got better values. Let's say 2 knows better values than 1. Then he will update all his neighbors. After that 3 might update all his neighbors, correct? So if that is the case, how many times in the best case, I mean in the worst case, how many times the neighbors got updated? Every time, let's say. How many edges we have? Every edge is teaching someone, let's say. Okay. So through this edge, 1 is teaching 2. Through this edge, 1 is teaching 5. In that way, every edge teaches someone. Then how many edges we will have? After all, E. Then how many relaxations will be successful? E. Not more than that, correct? Remember it. So now I can say that you traverse the list in the process, in the relaxation process. Then you applied that formula, relaxation formula. That took only E time because there are only E edges. But there is one more thing. We updated this D values in this relaxation process. But how many times you update? At most E times. For every edge, at most once. That is what I was telling. So it takes E units. I am directly calculating the time complexity. E units for updating D. Whenever you update D, someone learns a new information. We update pi value also. Correct? That takes E units. Doesn't matter. So P plus E plus E. E for what is this E times? E times is nothing but this relaxation formula, applying that condition, whether d of u plus weight of u will less than something. So that E and updating D, E times, updating pi, E times. So finally it is all E. Plus one more complex step we are doing. If some D value is updated, immediately go to the corresponding heap and update that value in the heap. So what's big deal? The big deal is whenever you update something in heap, that is called decrease key operation, right? So why it is decrease key? Because initially always you are reducing the value, whatever the heap value you have. Let's say this is your heap. In our process, we never increase the value of the key. Example, this key value 5. In this process, we always have a better value, correct? Distance of u will not be increased at any time, correct? We know the logic for that. In the relaxation step, always we keep our value, I mean old value, otherwise we get a smaller value, correct? So that's why, so always example, initial d of some x is 6. Then because of this relaxation, 6 might become 4 or 3, otherwise 6 will be 6, correct? If 6 is already, 6 is again 6, we don't update, otherwise we decrease it. So that's why usually we say decrease key operation. How many decrease key operations we do? If every time when you relax an edge, you might decrease the key, correct? So E times you do that, we know that. So what is the time complexity of decrease key? If you decrease the key, then heap might get disturbed, then we have to adjust. So heap adjustment takes log v time, we know that, correct? So we know how to update the heap, correct? So log v. How many times we do that? E times. Because every time, let's say heap gets updated, then E times, E log v. Let's summarize now. So in this relaxation step, V plus E for traversal, E for that comparison. What is that comparison? Distance of u, that's it. then E units for updating D values and E units for updating pi values. After that, the last step is updating in the heap E times, each time take log V, that's why E log V. So we did not do anything other than this, right? After all, we did these steps. So we'll see the time complexity of that's by Dijkstra. What are the major things we did? One is E log V. When you have E log V, we don't need to take E, correct? So doesn't matter. Plus we have V, correct? So E log V plus anything else. Here we deleted. Did you remember this one? This is also very big thing. V times we deleted a vertex from the heap. At that time we took V log V, correct? These are the important things, right? Let's summarize. See, V, and one more thing, initialization of this membership, everything took V, correct? V doesn't matter. So overall these two are very big things, correct? E log V plus V log V. All other values are V's and E's. So no matter how many E's we have, no matter how many V's we have, E log V dominates E, V log V dominates V. So you end up with E log V plus V log V, like Prim's algorithm. So I can say that it is E plus V into log V. This is the time complexity of Dijkstra algorithm. Okay. Now we'll summarize shortest path algorithms. We have two shortest path algorithms. One is Bellman-Ford and Dijkstra algorithm. So we'll try to compare them. Time complexity of Bellman-Ford algorithm is order of EV and it is E plus V log V, right? So EV is greater than E plus V log V. So time complexity wise, Dijkstra algorithm is better, far better. But the only problem with Dijkstra algorithm is if a graph contains negative edge weights like this. Example, here C to B, it is -5. But there is no negative weight cycle. If there is negative weight cycle, then definitely we cannot define shortest path problem. But it's not the case here. Here we have one edge whose weight is -5. But here still every vertex has shortest path. Okay. Now in this case, still Bellman-Ford works. We know that, correct? But Dijkstra algorithm will not work. The reason we'll see. The reason for this is, first of all, we fix the vertex, right? So that will be A. Now we are going to relax all the edges of A. When you relax all the edges of A, so B is going to get what? 0 plus 2, which is 2, correct? 0 plus 2. And C is going to get 0 plus 5, which is 5. After that, what we do? Again we close the vertex or fix the vertex. Next, this time, what is the vertex which we are going to close? B, correct? And we are now saying that in Dijkstra algorithm, so B is the vertex which is closed and it is already found the shortest path, but it is not the case. Do you think that 2 is the shortest path from A to B? No. So Dijkstra algorithm says that D of B is, 2 is the shortest path. That's why it is closing it. Based on that, it is deciding others, but it's not the case. Why? See this one, A to C, C to B. So 5 plus minus 5, 0. Later you will find that shortest path from A to B is 0, correct? But at this moment B is closed. But in Dijkstra algorithm, whenever a vertex is closed, that has to learn shortest path. But now B is not learning it. That means it's doing wrong. So Dijkstra algorithm will not work here. You run this entire algorithm. Okay. So that's why for this kind of problems, Dijkstra algorithm will not work. So blindly remember, if a graph contains a negative edge weight, definitely don't run Dijkstra algorithm. The reason it might not work sometimes. Okay. So this is about Bellman-Ford and Dijkstra algorithms. Okay.